Yeah, before we further go into the drives, it's better we recall some of the basics of the DC motors. Okay, so yeah, one by one we will just go through them. Okay, so whichever is required for us, those motors we will discuss. Okay, first one is separately excited DC motor. Excited DC motor. Okay, so you just see this now. Just recall that what is a separately excited DC motor. In the separately excited DC motor, the excitation is from a separate supply. Excitation in the sense, uh, this is your armature. This is your armature, and this is your field winding. Okay, so the connection, there won't be any connection between armature and the field. There won't be any connection between armature and the field is separately excited from the armature. So that kind of DC motor you call it as separately excited DC motor. So if you recall the basic equations of this motor DC separately excited DC motor, we will get some conclusions. Okay, let me take this is the armature voltage VA and this is field voltage VF. Okay, so of course there is no interconnection between VF and VA, so that is the reason we call this as separately excited DC motor. And the EMF induced in the armature is back EMF. I will tell it is EB. Okay, then what is the relationship between VA and EB? What is the relationship? If you recall, the relationship is this, it's only the recalling of the previous subjects. It's nothing new. Okay, so if you recall, we can write the KVL that VA is equal to IA RA plus EB. So what is IA here? IA is the armature current. Okay, whereas RA is armature resistance. This is armature resistance. Whereas EB, I said just now, it's a back EMF, and VA is the armature voltage. So you are supplying some armature voltage, or you are supplying voltage to the armature of the separately excited DC motor is how much? It is VA. Then, as per the principles, back EMF will be induced, and that is EB. And what is the relationship between these two is VA is equal to EB plus IA RA, where IA is the armature current. I will write here. This is armature current IA, and you will get the equation VA is equal to EB plus IARE. Okay, and some more equations I would like to recall now is that you see now, see here. Okay, so if you recall the equation for a back EMF, okay, several ways you can represent the back EMF. Okay, so I will write that here phi z. This is the equation for the back EMF of the DC motor. Phi is the flux, that's the flux from the excitation, that's field winding. Z is the number of conductors. N is the speed in RPM. P is the number of poles. A is the number of parallel paths. So these things I don't need to tell more. It may require here. So what I would like to do here is that, see, phi, so for the separately excited DC motor, phi is constant because you are not disturbing the VF here. Okay, so phi is constant. And Z, the number of conductors in the motor are also constant. P, number of poles, A, everything is constant except the N here. So I would like to represent this entire thing with a constant. So EB is equal, I will take one constant which has been using. Okay, so or we can do one more thing, that if there is a possibility, we will put only these are constant, so I would like to write that ZP by 60A into phi into n. Okay, so okay, this is one way to represent. Of course, in separately accelerated motor, a DC motor phi is constant, but even though I would like to represent in some other way that I will write this as kt phi, okay, into n. So what is kt here from this equation? Okay, kt can be written as kt is equal uh, ZP by 60 into A. So this is the thing you must remember while we do some more simplifications in this. Okay, and I can write further this. I can write this further. So how can I write this further? Is that so if we got an equation EB is equal to KT into phi into N. Okay, so I want to represent this further. So see this now. So I can write. See, there is the relationship between omega, okay, omega and n. What is the relationship? 2 pi n by 60 is omega. Okay, so this is the relationship you will get. Then what is n from this? N from this is that n is equal to 60 omega by 2 pi. So this is n value. Now we will substitute this n here in this equation. Then EB is equal to KT pi into 60 by 2 pi into omega. Okay. So now I want to rewrite this equation once again here. That is EB is equal to, now you see here 60 is constant, 2 pi is constant. See, if I take phi is also constant, because in case of the some motors your phi is constant. Some types of motors phi is constant. In case of separate accelerated DC motor, phi is constant. So I want to represent this equation now. Which equation now? This equation. This equation. This equation I want to represent in some other way. That is some Km into omega. This is another equation. See, you got one equation here. EB is equal KT into phi n is one equation. Of course, both equations are same. Only that in terms of which parameters you are representing that. That's important. So then, what's next then? So then, what is Km from this equation? Km can be written as KT into phi, okay, or 60 KT5 by 2 pi. This is Km. So, so we got the expressions for, so we only represented the back EMF into two different forms. One form is EB is equal to KT into phi n. Another form is EB is equal to Km into omega. So now remember, these equations are for separately excited DC motor. Maybe they may be true for the remaining types of motors also. So whenever we get, we'll just know about that, then we will understand that. Okay. Then what's next is that now you see here, you see, so we got the, so now recall what is torque, what is torque equation. So I want to represent torque equation also. What is torque equation? So if you recall the relationship between power and torque, P is equal to 2 pi nt by 60. So everyone might have remembered this equation that this P is equal to. So what is P? P is the power. So T is the torque production. N is the speed in RPM. So we will write this further equation. What is power? I can write power as the multiplication of the see how the torque is produced in the DC motor. So you are applying some armature voltage VA. So because of that armature voltage, some current flows IA into the armature. Then because of these two, some back EMF will be produced, that is EB. Now this back EMF, okay, the power from this one, okay, will go and it will drive the load. Okay, it will go and drive the load. So that one, that force or that torque, that one is called as torque, electromagnetic torque here. So how can I write that torque here, electromagnetic? So we got one equation, P is equal to 2 pi nt by 60. So now P I will write as EB into IA. Why I will write EB into IA? Please see this now. You just recall this equation. So IA is the current flowing into the armature. Okay, you can represent the armature also in some other way. Like I have seen, I have explained that already. That there is a resistance is there in series with the armature. That is also there here, RA. Okay, so this back EMF is there. So this back EMF. Okay, now this is the motor. So this armature is coupled somewhere. That I didn't draw. Now I'm going to draw that. This armature is coupled to some load, so mechanical load. ML. ML is the mechanical load. So this armature is connected to mechanical load. Then the product torque production in this armature will drive this mechanical load. So who is responsible for this torque now? The power in this is responsible. So what is the power in this? The power here is voltage. That is which voltage you will take here? Back EMF you will take. You don't take armature. You don't take the armature voltage because this is the entire armature voltage is not going to the armature. Okay, the terminal voltage which you are giving here VA is not totally going to the armature as back EMF. There is in between another term is there, that is the drop across the armature resistance is also there. So because of that, the voltage here which you will take is that EB is the voltage. So power is equal EB into IA. Okay, IA is the current flowing. So that is equal to 2 pi NT by 60. Okay, so we can write this further. So how we can write this further is that already we have represented EB in one particular form. In one particular form we have. What is that form? You recall that? So this is one form. This is one form. EB is equal to KT into phi n. This is one form. So we will use this form here. So if we use this form here, so it becomes KT into phi into n into I'm just writing EB from this equation. That is KT into phi n. So into IA. So that is equal to 2 pi n t by 60. Then how can I write this further? Yeah, how can I write this further? You see here. So this n will get cancelled. Let me simplify this. Here you have n, here you have another n. So both will get cancelled. Then what is t from this? T is equal, yeah, so kt into 5, kt into 5, or I will write here 60, 60 kt into 5 whole divided by 2 pi. Now you see here once again, 60 kt5 divided by 2 pi. Okay, so nn will get that is equal torque. Now you multiply with armature current is also there. You should not forget that thing. So armature current IA. Okay, this is the equation you got for the torque. Now this equation we can simplify further, because why I'm saying is that what is Km from this equation? You see the Km. This is Km. You see the Km here. Km is 60 kt5 by 2 pi. So the same thing is here. So then I can write it as like this. T is equal to some Km into Ia. This is the equation you will get. See, this is possible when you consider the flux is constant. So this is the equation between the torque and the current. This is the equation between the torque and current. So if I want to draw the relation, if I want to draw the graph between torque and current, if I want to draw the graph between torque and current, this is Ia I will take, whereas this is T. What is the equation you got? T is equal to Km into Ia. Km is a constant. Okay, because why it's constant? You see the terms there in place of the Km. So you will find out everything is constant there, because this is a separate lecture DC motor. Phi is also constant. So you get the relationship between torque and current is torque is directly proportional to the current. So if torque is directly proportional to the current, which type of graph you will get here? You will get a graph, a straight line passing through origin. So this is the relationship between torque and current in the separately excited DC motor. Okay, now we'll go further. We'll go further. Okay, so where is that equation? We will recall this equation here once again. Okay, so this is one graph we require. See, all these graphs we require to understand this DC drives. Okay, so now see that equation I will recall once again. VA is equal to EB plus IARE. This is the basic equation we have started with. From this equation, what is EB? EB is equal to VA minus IARE. This equation we got. Now, how can I write EB here? You just recall. EB can be written as in two ways. I told you already that one is that EB is equal KT into phi n, that is one form. The other form is EB is equal Km into omega. This is second form. So I would like to take the second form here. Okay. Then Km into omega is equal VA minus IA RA. We got this equation. Once we got this equation, then let me simplify this. Then what is omega from this equation? From this equation, what is omega? Omega is equal VA by Km minus VA by Km minus IA RA by Km. This we got. Then we will further simplify this. Omega is equal. Okay, so how can I write this? Yeah, I want to write this as something, okay, useful. Okay, so VA by Km minus, okay, so now if you look at this equation, which equation? T is equal Km into Ia. We got one equation here. The torque in the separate excited DC motor, that equation we got T is equal Km into Ia. So from this, what is Ia? Ia is equal T by Km. So that I will represent here. It is T by Km. So T by Km. So T into RA by Km, it becomes Km whole square. So this is the expression for omega we got. So omega and torque. So now remaining all the things, you see now remaining all the things. VA is the armature voltage, it is constant. Okay. So and RA is constant, everything is constant. So only two variables are there in this equation. What are the two variables? Omega and T. These are the two variables it has. Now I am interested to draw the relationship between these two, omega and Tm. So this is omega and T. Okay, this is what I interested right now. Okay. So now you see here. Yeah. So what is the graph you will get? Just go through the graph now. So use this equation, then we will get the graph easily. So we'll draw the graph between these two. Okay. So here I will take omega on y-axis and t on x-axis. Then what is the graph you will get here? You just look at this. If you look at this, this is a constant one. This is a constant one, and this is also constant one. So it's a straight line. Definitely, it's a straight line. But which kind of straight line here? You get a negative slope here. You see the negative slope between omega and t. So, or else you just start with something. You take t is equal to 0. Then if you take t is equal to 0, you will get a value here. So that value I will draw here. I'm just drawing the graph for this equation. This is a straight line. Why I'm saying it's a straight line? Because everything is constant except omega and t. So, and you see the relationship, it's a linear relationship is there. Then another graph is that this time we'll take omega is equal to 0. Then we'll get so something. So you draw now. See, I'm just drawing the graph, nothing else is there. So this is the relationship between, or this is the characteristics between speed and torque in the separate axle DC motor. So this is, first one is that it's between torque and armature current. Second one is speed and torque. Between these two, we have drawn the graph. Okay. So now this is about briefly about the separate axle DC motor. Now we'll go to another type of DC motor which we require in here. That is DC series motor.
Sir, is omega proportional to speed, sir?
Yeah, please tell omega.
Proportional to speed.
Yeah, omega, you have this equation. You see now, omega is equal to
Yes, sir.
2
2
pi
pi
n,
NTB.
2 pi n by 60. Am I correct? Is this omega? This is the
Yes, sir.
angular speed and this is the speed in RPM. Okay. So 2.60, both are constants. So you can say like this, omega is directly proportional to n. Okay. So I am drawing the graph between omega and t, in the sense it is nothing but the graph between uh, t and n. Am I correct? It is the graph between t and, because omega n both are directly relationship. So we can say this thing, that it is the graph between speed and torque. Am I correct?
Okay, sir.
Okay. So then we go further. So we will go to DC series motor and we do the same analysis. Same analysis in the sense we will find out the relationship between torque and current and speed and torque. So this relationship will go once again. Okay. So now you recall what is the series motor. So what do you find out in the series motor? In the series motor, unlike your separately excited motor, in the series motor, what do you find out is that so you will find out that the field is connected in a series with the armature. So you give the supply from here. This is how you find out in the series motor. So the you see the field is in series with the armature. This is the connection. So if in that case, once again, this is the armature voltage VA and this is EB back EMF. What is the relationship between armature voltage or the terminal voltage and the back EMF? So you will write that EB plus this time I will write as RA plus RF into IA. Why I am writing RA plus RF is that because this is the field winding whereas this is the armature winding. So both are in series. So it has the resistance of RF whereas it has the resistance of RA. As it is a series motor, both are connected in series. So the total resistance is RA plus RF and the current which is flowing here is IA. So simple KVL if you apply here, then you will get this equation. VA is equal to EB plus RA plus RF into IA. This is the equation you will get here. Okay. And then now what about the flux in this particular is the flux constant in this case of DC series motor? No, the flux is not constant. So this is the point you must keep in your mind. Why the flux is not constant? Because the flux depends upon the armature current, because the armature current as it is a series motor, the armature and field winding both are in series. So whatever the current flowing in the armature, in this case, in this particular picture, if you see whatever the current flowing in the armature, same current is flowing in the field winding. So as the armature current is IA, the field current is also IA. So the flux produced in this field winding or the flux in the DC motor, DC series motor, it depends on the current flowing in the field winding. Here the current flowing in the field winding is same as armature current. So I will write something like this, that phi is equal kf into ia. Okay, it means your phi flux depends on the armature current, whereas kf is a constant. So you can derive that constant. Okay, so we can say this thing that flux is directly proportional to ia and kf is the proportionality constant between phi and ia. This is another equation. And then we'll go further now. So what we do is now we will recall the torque equation which we got here. What is the torque equation we got here? So better I will just copy this entire equation. Okay, so copy this equation here and I will bring here this one. Yeah, I just bring the torque equation here, the previous torque equation. So now what you must understand here is that what is the thing you must understand is that now this equation which we got earlier, that is T is equal to Km into Ia, this is the equation when you consider flux is constant. But now in the case of DC series motor it is not correct, so we will delete this equation. We don't want this equation. Okay, then what is left now? T is equal to 60 kt 5 by 2 pi. So then we will write this thing. Okay, how we will write here is that, okay, so that is equal to, now you see here. So phi, now this time phi has a proportionality constant because phi is depends upon Ia. So I will write this phi in this particular equation. Then 60 into kt into kf into Ia by 2 pi into Ia. So now you see here now. All these are constants. Please see this now. 60 kt is a constant, kf is constant, 2 pi is constant. Only Ia into Ia is left here. So torque is equal to this. So then torque equation is equal. Okay. So yeah, I will represent this as some other name we can give. So I will let Ks. It's for convenient purpose, nothing else. So then Ia square. So this is the expression or this is the relationship we got between between torque and current. between torque and current. This is the expression we got. Okay, so this is the expression. So T is equal to Ks into Is square, where Ks is the constant. So with this equation, if we draw the graph between the current and the torque, like how we did in case of the separate accelerated DC motor, okay, so T we will take here, then Ia we will take here. Then what is the equation you will get if I draw the graph? Now this time it's not a direct, it's not a linear relationship between torque and current. So no, you see now T is proportional to Ia square. T is proportional to Ia square. Okay, so then in that case, what is the graph you will get here? So you will get a parabolic graph, something like this. I will draw. Okay, we are. I am not sure whether we call that as a parabolic graph or a hyperbolic graph. But only thing which we know here is that, yeah, you different values of Ia you take, then you draw the values of T, then I'm sure that you will get a graph something like this. Is the relationship between torque and current in case of the DC series motor. Okay, then we'll go further. So we would like to know the relationship between speed and torque in case of the DC series motor also, that also we are going to derive now. So to do that, once again we require this equation. Which equation we require is that, yeah, omega. So okay, anyhow I will do that once again. There is no problem in that. So what is that equation is that, once again we'll start with this. Va is equal to Eb plus Ia Ra. We have this now, this time Ia into Ra plus Rf, that's important. Okay, and then what is Eb from this? Eb is equal to Va minus Ia into Ra plus Rf. This equation we got. And then what's next is that, how can I write EB here? That's the question. How can I write EB here? So EB, okay, we recall the EB here. Okay, it's better we recall the EB. So you have two kinds of equations for EB. So which one here is that? Yeah, one is EB is equal to Km into omega. That is when you think phi is constant. When you think phi is constant. But now this time phi is not constant. You know this thing very well. So then we have another equation, that is Kt into phi into n. That equation will bring here. So Kt into phi into n. This is EB. So that is equal to Va minus Ia into Ra plus Rf. Yeah, then once we got this equation, then we have another thing. So what is phi from this? We just recall, because in case of DC series motor, we got another equation for phi, that is phi is equal to Kf into Ia. So this entire mathematics is there, nothing else is here left. Okay, only thing is that you have to substitute all the equations. That is equal to Va minus Ia Ra plus Rf. And then okay, we will do one thing. Okay, what we are going to do is that we will put n this side, then we will send the everything on the right hand side. Then it becomes Va by Kt Kf into Ia minus Ra plus Rf by see Ia will get cancelled. So Kt into Kf. We got this equation. And then we got one important equation in case of the torque. What is that? T is equal to Ks into Ia square. So we substitute that here. Then N is equal to Va by, okay. So what you will get here is that Ia is equal to square root of T by Ks. So square root of T by Ks. So this Ks will come here divided by Kt Kf square root of T. minus Ra plus Rf by Kt Kf. Okay, then N is equal. We can simplify this further. Okay, so what is Ks we have taken here? What is Ks we have taken? So Ks is that something we have taken here. Ks I will write here. This one is Ks. So this is Ks. Okay. So either we can substitute the Ks here or we will leave this equation as it is. So, okay, there is nothing problem in that. So then in that case, what do you get the equation here? That is VA is constant, root Ks is constant, KT, KF is constant, and this entire part is constant. Then what is the relationship here? You see N is equal to here and here N is inversely proportional to root T. So root T. In that case, the equation, so this is also it is also not a linear equation. It is also some more another equation. So in that case, how do you draw the graph between a speed and torque? So only thing is that yeah, you can substitute that yourself. That if I substitute t is equal to 0, then it becomes n is infinite. So somewhere you will get here, somewhere you will get that value. Okay. Then when I substitute n is equal to 0, then in that case, yeah, in that case of some, so you will get a graph something like this. If you take different values of n and t, you will get a graph like this. So this is the relationship between speed and torque in case of now you see here at lower speeds, the torque is very high. You just see the DC series motor at lower speeds, because from this graph the lower speed is here. So what is the torque here? If you see the line, if you see the line here, what is the torque here? Torque is very high. You see it is not intersecting here. It is intersecting at very okay, at long distance. So it means torque is very high. So at lower speeds, torque is high. Torque is high. So lower speed in the sense what generally during starting of the DC series motor. During starting of the motor, the speed is lower. So during the starting of the DC series motor, its torque is very high. That is the feature of your DC series motor. From this graph, you can understand that. Okay. Okay. So this is about separately excited DC motor and the DC series motor. And now some more motors are also there in the DC machines. We will discuss whenever we require. Right now, we require only these two. Okay, and then okay, uh, some more things also we require to understand the drives. So what are those things? Is that how do you control the speed of DC motors? Speed control of what are the methods? See, this is only something like refreshing ourselves the previous thing, so that we can go ahead and we can do we can study the drives effectively. So, what are the speed control methods? I think one is field control method. Okay. So what is the field control method here? So how the field is related to speed here, then we'll bring that equation. EB back EMF is equal to pi Zn by 60 into P by A. This is the equation we have for the back EMF. Now in this equation, you see flux is there and speed is there. How these two are related? They are related inversely related. You just see carefully. Your flux is here, your speed is here. So both are inversely related from this mathematical equation. So if you reduce the flux, you can increase the speed. That is the logic here. So reduce the flux. If you reduce the flux, it implies the speed will increase definitely. So this is the logic we will take in the field control method. So how do you reduce the flux here? What is the method to reduce the flux? See, to reduce the flux here, okay, say for example, for example, let me take separately excited motor. Once again, separately excited motor is there. What do you find on the separate excited motor? I told you already that the field and the armature. Okay, so the field is the field, and this is the armature. Okay, both are from different supplies. So it's very simple that so your field is there, your armature is here. So controlling the flux from this field winding can control the speed here from this mathematical equation, and both are inverse relationship. Uh, how do you control the flux here? So how do you control the flux here, or how do you control the field here? So you, if you have, let me bring this side here. This is the field winding. So if I connect a
Rheostat.
rheostat here, yeah, if I connect a rheostat here, this is a flux. So then by varying the rheostat, so this is the uh, field voltage. By varying this rheostat RF, by varying this rheostat, then the current in this field winding varies. That is IF varies. So if the IF varies, the flux production also varies. So this is the logic here. So by having a rheostat in series with the field winding, by changing the rheostat positions, okay, so you can change the current flowing in the field winding. So when the current flowing in the field winding changes, obviously the flux produced by that winding also changes. So if the flux changes, the speed can be changed. So this is the logic behind. Okay, in case of the separately excited motor, but in case of series motor, what is the problem? What is the difficulty is that series winding is in series with the armature. Okay, armature windings or armature it is. So this is VA. So in that case, how do you vary the flux here? That is the question. So to vary the flux, okay, several methods are there. Okay, several methods are there. One method is that field diverter. Okay, so field diverter in the sense, what do you do is that you connect a rheostat here and you vary the rheostat. So when you vary the rheostat, then the current which is coming here definitely will take two paths. One path is through the field winding, the other path is through the rheostat. So when I vary the rheostat, obviously the current here and the current here both varies when I vary the rheostat position here. When I vary the position of the rheostat, the current in rheostat and the current in field both will vary. It means somehow you are varying the current in the field winding with this field diverter. So in that case, what do you find out is that in that case, the flux developed by this field winding also varies because the current in the field winding varies. So as the flux varies, the speed varies. That's the logic here. So that's using the field diverter. There is another one is armature diverter. So armature diverter in the sense, what you do is that. So once again, I will redraw this picture. Armature. So this time you connect the rheostat here in parallel with the armature. So you vary this. So you vary the rheostat position here. So obviously the current here changes. So the current here changes. So the field winding current in the field winding also changes. So the flux developed by it also changes. So the speed changes. So this is the armature diverter. So diverter is nothing but you connect a rheostat. Okay, that's a diverter. So you are diverting the current to another branch. So that is the name you got the diverter here. So another one is that tapped field control. So tapped field control in the sense, see here, this is the field winding. So you connect the tappings here. So tappings in the sense something like this. I will show you here. Just show you here. Okay, so now you connect the supply here. So you give the supply at this point, plus minus VA, not here. So when you vary the position of this one, when you vary the position of this one, tapping, then obviously the number of tons will change. Okay, so the some things will change here. So when some things changes here, the current also can change, so the flux will vary. So this is called tapped field current, field control. So you vary the number of tons in the field winding, or you have some tappings, just like your center tap transformer, or just like your auto transformer, where you there is some tappings are there. So likewise here also, you do the tapping, you must have the tapping, then in that case it changes. There is another method, that is paralleling. Okay, so para paralleling field coils. So now paralleling field coils in the sense, see the field windings. If you go through exactly what is this field winding, it's a magnetic circuit. It's a magnetic circuit, and there is a magnetic core is there. So you have some coils like this. So now paralleling field coils in the sense, these coils, what you do is that instead of having only one single large coil, you will have more number of small coils, and either you connect them in series or you connect them in parallel. Here in this case, you connect them in parallel. So that you require, for that purpose, what you require is that you require some switches, something like DPST switches or DPS, these kind of switches you require. So these switches, sometimes you connect in position A, sometimes you connect in position B. So when you change the positions of the switches, obviously some coils will come in parallel. So when they come in parallel, obviously the flux developed also changes. So you see here, entire thing is that you are changing the flux so that the speed will change. So that's the thing. So what is the important thing? One parameter you must keep in your mind here in this, in case of the field control, is that, see, you can control the speed of the motor only above base speed. Why above base speed is that? You see here, flux is inversely related to speed. This you understand. Okay. Now you reduce the flux. When you reduce the flux, obviously the speed increases. So, and one more thing, why can't you increase the flux here? That is one more question you. So if you increase the flux, the speed may decrease. But what is the problem if you increase the flux is that it may go into saturation. Saturation. So field control method, only way it is left for you is that you reduce the flux. You cannot increase the flux. Of course, you can increase, but the problem you will face is that the magnetic circuit may enter into saturation. So if it enter into saturation, then all the problems once again will get repeated. So you won't go for that option, that increasing the flux. So you only have option is that decreasing the flux. So when you decrease the flux, obviously the speed increases. So you always increase the speed in case of the field control. That's the reason that I said that you control above base speed. Okay. So now you have another method, that is armature control or armature voltage control. So this time what you do is that this time, now like we have seen in case of the field control, that you have a rheostat, you have a rheostat. Okay, so that rheostat, this time you connect. Okay, for example, if it is separately excited motor, then it looks like this. So this time you connect the rheostat in series with the armature. In series with the armature you connect. Okay, so by varying this one, the voltage which is going to the armature of the DC motor will vary. So if the voltage varies, or so back EMF will vary, obviously. If the voltage which you are supplying here is varying, back EMF varies. If the back EMF varies, the speed varies. Why? Because back EMF, you see yourself now. Okay, back EMF and speed has a relationship that I don't need to tell once again, that EB is proportional to speed. Okay, so by changing EB, how you are changing EB? You are changing EB by changing the position of the rheostat here, which is connected in series with the armature. So change this value. So when you connect here, Obviously, see, when you don't have the rheostat, the total voltage will be applied across this. It means, for example, it is 200 volts is there. It requires 200 volts. Then if you connect the circuit without the rheostat, so total 200 volts will go. So the maximum value of EB will be there. But when you connect a rheostat, now you change the position of rheostat, then obviously the voltage which is going to the armature is always less than 200 volts. Why it is always less than? Because you connect a rheostat, definitely rheostat will it definitely will take some voltage. Uh, at minimum, it may take 0 volt, but other than 0 volt, it will take 1 volt, 2 volt, 10 volts, 50 volts. So whatever may be the voltage it takes, the remaining voltage only goes to your armature. It means the voltage which is going to the armature is always less than the total terminal voltage. So when it is always less than, then EB is always less than its actual value. So the speed is also always less than its base value. So speed is less than base value. So it means, what do you understand from this now? You understand from this is that the speed control in the armature voltage control method is always below base speed. Below base speed. This you must understand. So this is the armature voltage control method. Okay. So yeah, this is in case of separate lecture DC motor. This is in case of separate lecture DC motor. What about the series motor now? So even in case of the series motor also, same thing, no problem. That even in case of the series motor also, you can have this facility that that's it. So you connect here. So you vary the rheostat position. Then obviously the IA will change, EB will change. So and also the flux production also changes. You see here, in case of the DC series motor, if I vary the armature resistance here, not only the armature current but also the field current also changes. It means EB also decreases, phi also decreases. That's what I'm saying. Okay, or there is a agreement between, or there is a arrangement by changing these values. We will understand that. Okay, so this is in case of the series motor. Okay, what is the main problem with this armature voltage control is that there is losses in this rheostat, power loss in the rheostat. That's the main disadvantage of your armature voltage control method. Of course, the same rheostat you will find out even in case of the field control method also, but there the power loss is less. Why the power loss less is there is that the field current is generally less value compared with the armature current. So as the armature current is more, the power loss is also more, whereas the field current is less, so the power loss is also so this power loss is significantly more in case of the armature voltage control method. So this is one of the problem you will face with the armature voltage control method. Okay, now apart from this method, field control and armature control, there are some other methods also there, like you know, one thing I will tell you here, that this is the field winding, VF. Okay, you have armature. Okay, now you give the supply here. So rather than giving only one supply, see here, rather than giving only one supply, something I will do like this, that I have a switch here. So I have a switch here. So then I connect to one battery here. I connect to another battery here. So you have more number of voltage sources. Okay. So one, two, three. So you have more number of voltage sources than a single one. So in that case, either you can go, this switch may be connected to one, or it may be connected to two, or it may be connected to three. So by varying the position of this switch, the voltage which is going to the armature will change. So in that case also, you can control the speed of the motor. But what is the advantage here is that you don't have any kind of rheostats here. You will see here. So that is the advantage. So the power loss, the problem which you face, the power loss problem you will face in case of the armature voltage control method, that will not be here. Why? Because you are just only changing the position of the switch, whether it is V1 or V2 or V3, because different voltages are, multiple number of voltages are available here. So whichever speed we require, based upon that we will change that switch position. So this is one more type of uh, speed control of the DC motors. Now there is another method which is very famous one, that is we'll write here Leonard Ward-Leonard system. This is another one which is very accurate and very sensitive method of controlling the speed of your DC motor. So how we will control, you see now. So the logic here, simple thing, that this is your motor. Okay, this is your motor. This is your motor to which, for which you want to control the speed. So this is its field winding. Okay, so the field winding you are getting one supply here. Now assume that this supply is fixed. This supply is fixed. Now how you are getting the supply to your armature? That, so you are getting the supply to the armature of. So this is the, see, this is the motor to which you have to control the speed. Motor. I will write it as main motor. Why I'm calling it as a main motor is that you have some more motors in this particular method. Okay, so that one we are going to find out now. Okay, so for this motor you have to control the speed. So this motor has a field winding and its voltage is fixed. Okay, say for example, then the supply which is coming to this motor, to the armature, it is coming from a generator. Once again, it is coming from a generator. So the generator terminals are directly connected to the motor terminals. This is one important thing. And another thing is that one more problem you will face here, that so this generator is also, so this is also this generator. So this generator is also having a field winding. Obviously, this generator is having a field winding. Okay, so that one is coming from some other supply. We will see that from where. So this is the field winding of this generator. Okay, now, so what a generator requires? Generator requires a mechanical energy once again. So how you are getting the mechanical energy is that you are getting the mechanical energy from another kind of motor. So that motor I will draw here. This is another motor. I will write it as M2. So here you have two motors. It's very important. So that motor shaft is coupled to the shaft of the generator. So the mechanical energy, okay, so which is coming from another motor. Maybe it is a AC motor or DC motor. So for example, let me take the case of AC motor. Then it is a AC motor. So you don't need to worry about. So say for example, let's say induction motor or some other kind of motor. So we will give AC supply to the motor here. Then that motor will run. So that shaft of the motor will be connected to the generator. So you are giving mechanical energy to the generator, and also you have a field winding to the DC generator. So the generator will generate electrical energy. That electrical energy will go to the motor whose speed we have to control. So here the logic is, simple logic is that the voltage of this generator will be controlled. So if we control the voltage of this generator, it means you are controlling the voltage to your motor, because both are connected in parallel. You see this now here. So the voltage which is there from the generator, that voltage is going to the motor. So I want to control the speed of this motor, main motor. Then I want to change the voltage of this motor, because by changing the voltage to the coming to the armature of the motor, it can control the speed, or it can change the speed of the motor. So how I am controlling this voltage here? The voltage which is coming to the motor, as it is coming from the generator. So we will control the voltage of the generator. So how do you control the voltage of the generator? By changing the excitation from its field. This is the field here. It's important. So by changing the field excitation here. So how can I change the field excitation here? So then I will connect this to some other kinds of you know yeah, how do you control here? You will use the field control method here. Field control method, because you are controlling the field here. Or you have some other types of method. Or if you take electronics, you have a power converter. I can say power converter. I have a power converter. Something power converter here. Or I will say there are some phase control rectifiers are there in the power electronics. If you recall, phase control rectifiers. So using the phase control rectifiers, here we will connect the rectifier here. So the supply which is coming to the field changes. If the supply which is coming to the field changes, then obviously we know very well that in a generator, by changing the excitation, we can vary or we can change the output voltage of the generator. So the output voltage of the generator changes, so that output voltage goes to the motor as input voltage, so the input voltage changes, so the speed of the motor changes. So now what are the advantages of this method is that one thing is that the efficiency is better compared comparatively. Second thing is that you can control the speed of the motor accurately in the sense even a small variation also you can get in this type of method. The previous methods, the problem is that there is a power loss is there. There's a huge power loss is there, so the efficiency of the system is poor. This is the problem.